Topic 5. Energetics, Thermochemistry. 5.3. Bond enthalpies. Here you can find the objectives for this topic. Bond enthalpy. Now, bond enthalpy is the amount of energy required to break 1 mole of bonds in the gaseous state, and this is averaged across a range of compounds containing that bond. What that means is that we don't simply take, say, the CH bonds in a methane molecule. They'll take the CH bonds in a methane molecule, an ethane, propane, butane, pentane, hexane, and then any other molecule that they can think of, and they will average the CH bond enthalpy in all of them. Therefore, it's an average, and it's not going to be necessarily identical to an individual particular CH bond in one said compound. It will vary slightly. Now, breaking bonds is endothermic, so it will draw in energy, and making bonds is exothermic, so it will give out energy. So if the overall reaction is exothermic, the bonds have lost energy, are more stable, and have higher bond enthalpies. If the overall reaction is endothermic, the bonds have gained energy, are less stable, and have lower bond enthalpies. Now, using Hess's law and bond enthalpies to determine enthalpy of reaction. Now, to determine delta H, we take the sum of the bond enthalpies of the reactants and subtract the sum of the bond enthalpies of the products. Now, we can see this in the diagram at the bottom. So going from reactants to products, we need to go via the gaseous atoms. And this leads us through the bond enthalpy of the reactants to gaseous atoms and then the products to gaseous atoms. So we're creating a path through. So we're going from the reactants to the gaseous atoms, and then as we need to correct the arrow direction, it's the negative of the bond enthalpies of the products. Now, this diagram here shows us going from reactants to products. Now, this reaction here would be an exothermic, as the delta H is going down, so we're giving out energy. Now, the green you can see is the sum of the bond enthalpies of the reactants, and the light blue is the sum of the bond enthalpies of the products. And it is the difference that we're interested in. It's the difference that overall will give us our enthalpy change. Now, in your data booklet, you're going to see a large table with lots and lots of different bond enthalpies. Now, these bond enthalpies are measured in kilojoules per mole, and that's for single bonds. So if you look at, say, bromine-bromine, which is 193, H2I, which is 298, they're for single bonds. Below this table, you will see the bond enthalpies for some double bonds and triple bonds. Now, our first problem, calculate the enthalpy change for the reaction, stated here. Now, this is a famous reaction. This is the Haber process, where we make ammonia from nitrogen gas and hydrogen gas. You can see the ratio is 1 to 3 to 2. Now, it's going to involve using our data booklets. So we're going to find first off, let's start with the reactants. Now, nitrogen exists diatomic and is a nitrogen-nitrogen triple bond. Okay, so you should know that from when we looked at covalent bonds. Now, in your data booklet, this has a value of 945 kilojoules per mole. Now, there's only one of them. Okay, so we don't put the one there, but there's that imaginary one in front of the N2. There are 3 H2s, and hydrogen, again, it's diatomic, but there's only a single bond between there, because there's only one electron needed to complete the shell. There are 3 of them, and the value from the data booklet was 435. If I just quickly scoot back, we can see HH, 436 there. Okay. This example is just slightly rounded differently. We can see we need to multiply that value by 3 due to the 3 moles of H2. And we can add all these up. We then need to look at our bonds formed. Now, in NH3, there are 3 NH bonds. We can look them up on the table. But there are 2 ammonia molecules, because there's a 2 in front of the NH3. Therefore, whilst there's 3 in the molecule, there's 2 molecules overall. So it's 6 NH bonds in total. Again, we can add all this up, and then it's simply reactants minus products. And this will give us our overall enthalpy change. And as we can see, this is an exothermic reaction. Now here, we're looking at the bond enthalpies of ozone. Now, ozone is decomposed more easily than oxygen. So O2, which is oxygen-oxygen double bond, requires 498 kilojoules per mole to break, whereas O3 requires only 364 kilojoules per mole to break. And the reason for that is we have this moving of the double bond. It's almost 1.5 bonds because there are 3 oxygens joined in a row. Each of them have a single bond, but one has a double bond, and then the double bond flips. So it's almost a partial bond across the whole thing, which we can see drawn with a dotted line across. So therefore, it's less than it would be for an O2 double bond. Now, energy profile diagrams show that ozone molecule is more stable than an oxygen molecule with an oxygen radical. What that means is if we go from the O3 reactants to the O2 product, when we form the product, it is an endothermic reaction. We're forming very, very stable products. Now, when you can see the O on its own, that is something called a radical, and we will be looking at radicals in more detail later. Now, EA is the activation energy, so we're inputting a certain amount of energy to get us started. But the products have more energy than the reactants, and that is reflected by the value needed to break the bonds. Okay. Here you can see the objectives for this module, so please do read through them again.